Have you ever stopped to think about the technology you're using right this second? Your phone, your computer, it all kind of feels like magic, doesn't it? Well, spoiler alert, it's not. It's physics. And we're not talking about simple high school physics. We're talking about the truly bizarre, counterintuitive rules that govern the universe at its smallest scales. In this explainer, we're going to pull back the curtain and show you the hidden quantum engine that makes our modern world tick.
So here's the big question, the one that kicks this whole thing off. How on earth does a strange little rule about how subatomic particles behave power the entire internet? I mean, really think about that. A tiny, weird quantum effect is the reason we can send data zipping across the globe in a split second. It sounds impossible, right? Well, that's the incredible story we're going to unravel together.
So here's our game plan. We'll start with the crazy new rules that basically broke physics. Then we'll see how we learn to tame the atom itself. After that, we're going to forge a literal super beam of light, turn it into a data superhighway, and finally, see how this all makes our quantum-powered world possible.
All right, let's jump in. Picture this. It's the late 1800s. Physicists are kind of patting themselves on the back. They think they've basically solved the universe. You had Newton's laws for big stuff, Maxwell's equations for light. Everything was neat and tidy. This was classical physics. But then they started running experiments that just didn't make any sense. The results were weird. It was like the universe, on its smallest, most fundamental level, was playing by a completely different rulebook.
And this really shows you the massive divide. On one hand, you've got classical physics. That's our everyday world, right? You throw a ball, you know exactly where it's going to land. It's predictable. But then you have quantum mechanics, and that's the world of the super, super small. It's not predictable. It's fuzzy. It's all about probabilities and uncertainty. It is a completely different, almost alien reality that's hiding just beneath the surface of everything we see.
Okay, and this is where your brain might start to hurt a little, in a good way. For ages, everyone agreed light is a wave. Simple. But then, some new experiments showed that, wait a second, sometimes it acts like a little bullet of energy, a photon. So then, this physicist, de Broglie, comes along with this totally wild idea. He says, okay, if light waves can pretend to be particles, what if particles, like electrons, can pretend to be waves? And boom, this absolutely mind-bending concept, wave-particle duality, becomes one of the pillars of this whole new science.
And if you thought that was weird, get ready for this. This is maybe the most famous rule in all of quantum physics, the Heisenberg uncertainty principle. And what it says is, you can't know everything. It's literally impossible. The more you nail down where a particle is, the less you know about where it's going, and vice versa. And here's the kicker. This isn't because our measuring tools aren't good enough. Nope. The universe itself has this built-in fuzziness. It's a fundamental law of reality.
Okay, so the quantum world is fuzzy, uncertain, and just plain bizarre. But discovering that wasn't the end of the story. Oh no, that was just the beginning. The next step was, okay, this is weird, but can we use it? Let's see how scientists went from being baffled by these rules to actually harnessing them to do some incredible things.
And the secret, the real key to all of this, was figuring out how light and atoms, well, how they talk to each other. It's this constant little conversation happening everywhere, all the time. And once we cracked the code of that conversation, well, that unlocked everything.
Turns out, this conversation has three main parts. First, an atom can just absorb a little packet of light, a photon, and get all energized, kind of like drinking a cup of coffee. Second, that energized atom can just randomly spit the photon back out. That's called spontaneous emission. It's totally random, totally chaotic. It's basically how a normal light bulb works. But that third one, stimulated emission, that one is the game changer. That's where the magic is.
Yeah, let's focus on this for a sec, because this is the whole secret sauce. With stimulated emission, you take an atom that's already hyped up on energy, and you tickle it with another photon, and what happens is amazing. It doesn't just spit out a random photon. No, it spits out a perfect twin of the one that poked it. Same direction, same energy, perfectly in sync. It's a copy machine for photons. So one photon goes in, two identical ones come out. Those two hit other atoms, and now you have 4, then 8, 16. You get the idea. It's a chain reaction. This is the quantum engine of amplification.
Okay, but there's a catch. For this awesome chain reaction to work, you need a lot of those energized atoms just waiting around, ready to be copied. The problem is, in nature, most atoms are lazy. They're in their low-energy ground state. So we have to create a totally artificial situation where you have more excited atoms than lazy ones. This setup is called a population inversion, and figuring out how to do that is what makes this whole thing possible.
All right, so we have our quantum trick, stimulated emission. We have the condition we need to make it work, population inversion. So what happens when you put them together? You get one of the most incredible inventions of the 20th century, the laser.
So what's the recipe for a laser? It's actually pretty straightforward when you break it down. You need 4 things. First, your active medium. That's the stuff with the atoms you're going to get all excited. Could be a gas, a crystal, whatever. Second, you need a pumping source. That's just a fancy way of saying you need to blast it with energy to get that population inversion going. Third, you need something called a metastable state. Think of it like a holding area, where the excited atoms can hang out for a bit, making it easier to get that chain reaction started. And finally, the secret ingredient. You stick the whole thing between 2 mirrors. This optical cavity traps the photons, bouncing them back and forth through the medium over and over again, building up this massive, perfect avalanche of light.
And look at the difference this makes. The light from a regular light bulb, it's a total mess. It's like a crowd of people all shouting different things and running in every direction. But laser light is different. Because of that perfect quantum copy machine, you get a beam that's super focused, incredibly intense, and perfectly coherent. That just means all the light waves are marching together in perfect formation, like a disciplined army. It's order created from chaos.
Okay, so we've built our incredible super beam. Now what? How do we use this perfect, orderly light to send, cat videos across the ocean? This is where we build the light superhighway.
And the secret here is actually a much older, simpler physics trick called total internal reflection. It sounds complicated, but it's not. All it means is that if you shine light through something dense, like glass, at a really shallow angle, it gets trapped. It bounces off the inside surface instead of escaping. And the amazing part is that it reflects perfectly. Almost no energy is lost, which means you can send a beam of light a really long way. And that's exactly what a fiber optic cable is. It's basically a super long, super thin tunnel made of glass. You've got the inner core and an outer cladding. All you need to know is that they're designed so that when light tries to leave the core, it hits that boundary and just can't. It's trapped. So you take our laser and you start flashing it on and off super fast, creating pulses of light that represent the ones and zeros of digital data. Those pulses get shot into the glass fiber, and they just bounce their way down the line for miles and miles, perfectly preserved. And don't think this is some niche thing. The scale is, well, it's mind-blowing. Get this, over 95% of all data that crosses oceans, we're talking your video calls, your Netflix streams, international banking, everything, it's not going through satellites in space. Nope, it's traveling as tiny flashes of laser light inside these glass threads, thinner than a human hair, lying on the bottom of the ocean. So let's step back and just connect all the dots. We've gone from the weirdest corners of physics all the way to the global network that pretty much runs our lives. Let's trace that incredible path one more time. I mean, just think about the journey we just took. It started with a weird quantum rule about how atoms can copy photons. That discovery led to an invention, the laser, a machine that creates a perfect beam of light. And that perfect beam, when funneled through a glass thread, became the superhighway for nearly all the world's information. And that's the coolest part. This isn't just some abstract science lesson. It's real, and it's happening right now. The only reason you can stream this, the reason these words and images are reaching you, is because of that entire chain of discovery. A strange little rule about how atoms behave is literally what's powering your screen at this very second. So it all leaves you with one final, massive question, right? 100 years ago, grappling with quantum mechanics gave us the laser, which in turn gave us the internet. So, as we push even deeper into that weird quantum realm today, with things like quantum computers and new kinds of sensors, you have to wonder, what's the next world-changing discovery that's waiting just around the corner?